at our part C again. So we are at this unknown at x 0. So it says we have an ether flow. So after doing this unknown and putting this initial in here, we see that we have our ether flow, our alcohol flow, our exiting, our extent of reaction 1 and our extent of reaction 2. So these are all of the unknowns that we have, and we need to solve them, right? So this is just going to compile all of our variables that we don't know. So let's look down at equation 2. So we have that it says over on this side, it says combine the molar flow of the feed of the water and the recycled is 12 times that of the alkene molar flow rate, right? So let's come over here. So let's write this down. So this is going to be our Warfel constant. And that's going to stand for the water alkene reaction flow rate. Oh, it's reactor, not reaction flow rate. So it's going to be the water alkene reactor flow rate. Okay, so after we're looking at this, let's see. So this is going to be 12 times the amount of the flow rate. So we need to have, this is going to constrict our alkene flow. So let's write this down. We're going to write the Wolfer constraint, right? Because this is going to constrain our reaction, and it's going to restrain like the flow rate that we know of the alkene. Is the water in, right? So all that water being recycled. So we have our water flow rate. We have the water that's coming from the distillation chamber, and then we have our water that's being recycled from our azeotropic distillation, which is our decanter water, right? So all of these are going to be multiplied by 12 because there are 12 times the amount of our alkene flow. So we're going to divide all of these by it. So let's look at this. So we are gonna, it's 12 times the amount of the molar flow rate. So we're gonna divide all the water feed that's coming into it, divide it by 12, right? Because we need to add up all the water flow rates, and then when we divide it by the water, we divide it by the molar flow rate, then we should get it. So let's type in our first one. So first water, right? Oh, we're going to do water flow rate. And then we're going to do the water, but the backwater from the distillation feed, and then the decanter water. And then we're going to divide this by the alkene flow, right? And then we're going to subtract it by the Wolfer constant, which is 12, but we're just going to keep it in as one of our constants that we have. So okay, so the next thing that we want to do is, so we have this constrained, right? So we want to have this return. So what do we need to return from this equation? We need to return a big mass balance. So we are going to concatenate this. So NP dot concatenate. But we're going to use JAX for this. So we're going to have to use JNP, right? So we can see up here that we imported JAX NumPy, and we're going to use JNP as our concatenate. So let's go down here again. And so instead of using NP, we're going to use JNP. and this is going to be concatenate. And we're going to do a big flow. So the first thing that we need is going to be, so let's do our reactor balance. And we're going to put these all in here, and they're all going to give us some sort of variable, right? So they're going to give us multiple equations for this, and when we do the concatenating function, this will let us solve for multiple different equations. We're going to have a lot of equations. So let's do reactor balance, and then we're going to do the D1 balance, right? And then we're going to do our azeotropic balance. And then we're going to do our D1, our vapor-liquid equilibrium, right? And then lastly, we're going to use our Hw5C constant. And so one thing we know about the Hw5C constant is that it's only going to be one constant. It's not going to be 4 variables or 4 equations. So this is going to lead us to an issue where we're going to need another thing. Because if we look at the first 4 of it, they all have 4 equations for it. The reactor balance has 4 equations for 4 components. And the D1 balance has 4 equations for 4 components. It's the azeotropic as well. And then the D1 VLE also. So after all of that, what we're going to do is, that's going to give us 16 equations. We need to make this at least one. So what we're going to do is JMP, at least, and then 1 dimension, because this is a 1 dimension, because there's only going to be 1 equation for this, while the rest have 4. So if we look at it, it has 17 equations that this is going to solve. So this makes a lot of sense that we're going to use our dictionary. So we are going to have to define some of these functions. So let's go over here and let's define some of our functions. So we have our E dot D1, and we're going to do our flow first, right? So we're going to define our flow into our distillation. So do is, this is going to be a range because we're trying to find this. So the range of this, guess this as our alkene flow times our Hw5C constant, right? So this is what we guess it is going to be. And the minimum it can be is going to be 0 again, right? We're dealing with real numbers here. And then the largest it could be, what could the largest be? We're going to guess it could be only 2 times. We're going to get our guess. So our alkene flow and our Hw5C flow. So let's just copy this over here. And then the next thing that we want to define is our composition of our flow, right? And this is going to be the comp function to have the composition of it. And inside, we're just going to make some guesses of what the propylene, the ether, the alcohol, and the water are going to be. So we don't know what they are, but this is going to be kind of a guess of what we think this composition of our 4 components are going to be. And they are going to be still ranked in the same way we ranked them before. So we're not going to change any of that format. So what can we think about when we're thinking about the flow rate, right? Propanol, really low. Ether, because we shouldn't have many ether on that, and our alcohol should be low, and the majority of this should be our majority of what we want to do is, so the next thing that we have coming out of the system is going to be our backflow. right? So this is going to have a range, and we're going to do the range of this. So what is going to be our minimum maximum? It's going to be the same thing as our flow rate, right? So it can only be big as like our alkene. Our guess is our alkene times our Whf4 constant, but it's not going to be big as twice as our alkene, right? Times our Whf4 constant. So now we just want to do the composition. So the composition, so if we think about this, this should have a large quantity of water, right? And it should have so we have our propylene as 0.1, and then a guess that we can have is that our ether, our alcohol, and our water are about the same. So now it's going to be this. So let's change these numbers. Let's make our propylene really low, our ether really low, and our alcohol really low, because these are going to be filtered and go through the azeotropic distillation. The majority of it should be water. The majority. Okay, so the next thing that we want to do is going to be our distillate flow, because our distillate is also leaving our system. So let's do our distillate. And this is going to equal, so we're our range. So what is our range going to be of this? Should be. So if we think about it, we are having our propanol, our reaction 2, right, where our isopropanol is made out of 2 moles and our ether is made out of 1 mole. So since of that, we should divide our alkene flow divided by 2, right? So let's divide this by 2. I just copied and pasted that. And then it shouldn't be twice as big. So the next thing that we want to do is our composition of our distillate, right? So this distillate, we're going to guess, what should we guess as our components for this? Well, if it's leaving the system, it should have a large majority of our water, of our alcohol, of our ether. It should have a really low amount of our propylene, because that should be already reacted by now. So let's put 0.1 for our propylene, 0.33. Let's just say everything is even for the ones that are in the majority of this, right? So the next thing that we have left is going to be our decanter water. It is going to go back to the flow of the system. So our decanter water, let's think about the range of this. So what could it be the lowest and the minimum of this, right? So it should be the same as our distillate, right? If we're bringing 2 in and we're leaving, if we're bringing 2 moles of isopropanol in, we should be leaving the isopropanol out, right? So then let's just do our composition of this, right? So what is our composition of our decanter water? So let's think about this right now. So we have, we know that, so this means our water should be the highest, and there should be really low amounts of the other components. So let's just say 0.2, 0.02, 0.018, and then 0.98, right? Our water is going to take up the majority of this, because this is our last recycled water through, right? It should be the cleanest out of all the water recycled. This here should not be divided by 2, so we change that there. And now let's do some shift enter of this. So the thing we want to work on is our wrapped function. So we need to wrap our equation. So wrapped and then equal, wrap, and then we're going to wrap our second equation, right? Let's go down here, and we are going to use, right? And so inside we're going to have, so in our root function, we're going to have our, we're going to have a wrapped function. So let's write our wrapped in here. And we're going to have our x naught. And we're going to have our so we're going to use JMP, right? So we're going to use the Jacobian matrix to solve this equation, right? So this needs to be solved because, so we're going to use Jack as JX, and then we're going to use our Jacobian matrix, because our Jacobian matrix is going to allow it for a matrix to be made, and that is going to help us solve it's going to help us solve this function with like multiple variables and multiple different equations, right? So we have our function fixed up here, and I got the solution to converge. What needed to change was our wrapped function, and we had some inputs wrong up at the top that we needed to change so that those can converge. So right now, let's look at this. We want to look at x. X is going to be the thing that we want to look at on our thing. So if we see from this, we have this x2 unknown function right here. So let's do the unknown function. So x2 unknown. And we're going to put in our solution, right? So I made it equals the solution. So it's SOO. Equals our root function, so s dot x, right? So this is going to help us. So this is going to solve the x, and it's going to give as dict. We need to fix we need to put a dot here, and then we need to put parentheses marks here. So this is what we got when we converged it. So it gave us all of the things that we wanted to solve. Our ether flow, our alcohol flow, extent of reaction 1, extent of reaction 2, both of the flow rates going in, plus the comps and all of that. So this is going to help us because this is going to give us the answer, give us a float, give us the array, right? So we can see, yeah, it's giving us all these answers and our floats to it and our arrays to it as well. So thank you, that is the end.